Hi everybody. I'd like to make a quick video showing how to use symmetry. Symmetry of the up and down paths, the fact that gravity is always accelerating objects in the negative direction at a rate of 9.8 meters per second squared. I want to use this symmetry idea to solve problems. The problems I'm going to go over are these. It was how we introduced this. A student catches a ball 2.2 seconds after throwing it upward. How fast did she throw it? How high did it reach? Assuming she catches it, what's the velocity of the ball the moment before it strikes her hand? On the back side, we'll look at this problem that involves a kid jumping straight upward with some speed that allows them to get to a height of 0.48 meters. We're going to figure out how long they were in the air total and what speed they must have left the ground with. Again, the beauty of one of the things that's beautiful about acceleration due to gravity is that what goes up must come down. What you throw up at 12 meters per second comes down and hits your hand, assuming you're at the same height that you threw it up, at 12, up at 12, down at negative 12 for velocity. And that the time it takes to go up is the same as the time it takes to go down. This we will see is key in solving problems like this. Okay, so I've just made a little diagram of the situation. The kid throws the ball up, it eventually stops and comes back down, and it takes 2.2 seconds for this whole event to happen. Now you've gotten really good at using the 4 formulas of kinematics, making your list every time. In this case, it appears at first glance that you don't have enough information. I mean, you know the acceleration due to gravity is 9.8 meters per second squared in the negative direction, but you don't know either the initial velocity that was thrown up or the final velocity that it hits the ground traveling. You know they're the same, the absolute value of those numbers is the same number. You might want to put 2.2 seconds here because that is a time that's given. There are more difficult ways to do this, but really the easy way to do these types of problems is to what I call invoke the hand of God. That's my kind of cute way of saying, like, whip out your hog and hand of God, and why don't you drop the ball from there? Like, rather than start here and finish here, because you don't know either of these velocities, you know that the velocity at the top is 0. So if you choose to start at the top, it gives you a value that you already know. Now wait a second. The time that we wrote down that was given, the 2.2 seconds, that was the whole time up and down. But of course, it only takes half that much time to go up and only half that much time to go down. So if we want the truth about either the beginning or the end, we can't use the whole time. We need to cut that time in half. So the time it takes to go down is 1.1. Now you could make the final 0 and look for the initial, because that's kind of what the question asked. What speed did she throw it? But I know that these numbers are the same. This one's positive, this one's negative. I know that those V's are the same. So I typically tend to drop it. I like having the initial velocity 0 because it allows me to eliminate things in certain equations. They just disappear. So let's go ahead and find the final velocity that it hits the ground traveling at, and know that that number is just the negative of the speed that it really was thrown up. But again, just to emphasize, I'm starting in the middle of the whole situation at the top, using my hand of God to drop that ball. So we don't know a damn thing about the displacement. We know we want to find the final velocity. So we're going to use the equation that doesn't have x in it, which of course is the first equation. Because I dropped it, I can eliminate the initial velocity. It equals 0. And this just becomes v equals at. And that comes out negative 10.78. meters per second. I'm going to round that off to 11. And because I wanted the velocity that it was thrown up, then I'm just going to leave it as a positive number and call that a day. The second question is, how high did it go? So in this case now, let's change color to red. For the second part of the problem, what I'm looking for is this. Now I know that this final velocity is negative 10.78 on the way down, but I'm going to pretend I don't know that, because like I've said in the past, maybe you made a mistake calculating that number. If we can avoid using a calculated number for a second part of a problem, that's probably a good idea. So we're going to go ahead and pretend like we don't know the final velocity. That still gives us three numbers and a question mark, which always allows us to use one of the four equations of kinematics. This time I'm going to choose the equation that doesn't have final velocity in it. Of course, that's the third equation. X equals v naught t plus 1 half at squared. Again, I'm pretending to drop it. I like going on the downward direction, because when the initial velocity is 0, things get simple. This simplifies to 1 half at squared. And of course, we can plug in our values, not forgetting to square the time. And I get 5.929 negative. Now, of course, it's negative because I chose to start here and end here, and that's where it has been negatively displaced. X is really displacement from change in position. But the question is the height. And so height is a scalar, is never a negative number. It just doesn't have direction. Height is just a height. And so I'm going to round this off to 5.9 and leave it positive because I asked for a height. You don't measure your height typically as a negative number. Okay, so that's the problem on the front. Let's see if we can do the problem on the back. Okay, we'll hit this problem on the back. Recall that the question is, if a child jumps straight up with a speed that allows them to reach a height of 0.48 meters, what was the time that they were in the air, the total time in the air, up and down, and what was the child's speed when they left the floor? Okay, so I sketched a little sketch. We're at a point in the class where I think drawing a picture can often help you see things. We're at the same position we were a minute ago with the ball being thrown up and down. If we make a list of what we know and don't know and want to find out, we have too many things we don't know. I mean, you don't know these speeds. They're the same number, the final being negative and the initial being positive, but you don't know what that number is. You know the acceleration due to gravity is what keeps them from going up indefinitely and coming back down, and we want the time. But look, if you try to call this the initial velocity and this the final velocity, you got some problems. First of all, your displacement then would be 0 because you're essentially where you started when you finish. And so your change in position, your displacement is 0. So you can't use the 0.48 if you take the whole up and down trip together. So again, we're going to invoke the hand of God, so to speak. We're going to whip out our hog and drop this child from the height of 0.48 meters and see how fast they're going at the end of falling downward 0.48 meters. So we're going to grab that kid and drop them. By pretending to drop, we now know the displacement is negative 0.48 meters. Why negative? Well, because of course the displacement is downward in the same direction as the acceleration due to gravity. And now we have three numbers and a question mark, and one quantity that's not available to us, the final velocity. Of course, when that's the case, final velocity is not applicable. We use the third equation of kinematics. Displacement is equal to initial velocity times time plus 1 half at squared. Again, as I alluded to a moment ago, the beauty of dropping the kid from the top rather than trying to go on the way up is that this initial velocity is 0, and 0 times any time is still 0. So this simplifies to 1/2 at squared. Displacement equals 1/2 at squared. I'm going to solve this quickly for time. I'm going to multiply both sides by 2 to get rid of the 1/2. I'm going to divide by a on both sides so that I get t squared equals 2x over a. And now I'm going to take the square root of both sides to get my working equation for the time it takes to fall at displacement x. Plugging in my values, I get a value of 0.31298 seconds. Is that the answer to the question? Well, no. The question was, how long is the child in the air for the whole up and down path? We just found the time from the top down. So this is half the total time that the child was in the air. So the total time is 2 times that number. And I'm going to round that off to 0.63 and call it a day. The final question is, what was the child's speed when they left the floor? But again, that's the same number as the velocity they have when they hit the ground on the way down. So I'm going to drop this child again, but this time, instead of calling the final velocity not applicable, I'm going to ask what is the final velocity after they've fallen this distance. Now I could use the half the time, but again, I don't know for sure if the time I just calculated is right or wrong, so I don't want to subject myself to that kind of pain. Let's avoid using a number we just calculated, if possible. And it is, of course, possible because there is an equation that doesn't have time in it. It's the fourth equation of kinematics. Final velocity squared equals initial velocity squared plus the quantity 2 times acceleration times displacement. We're looking for final velocity, but we're dropping the child, pretending to. So this quantity, the whole v naught squared term, is 0. And this just becomes v squared equals 2ax. And of course, taking the square root of both sides gives me the square root of 2ax. And plugging in my values for a and x, I'm going to get. Now notice that the negative displacement and the negative acceleration, when multiplied together, produce a positive number. The only thing you can take a square root of, a positive number. So that's important to realize. Under the root, I get 9.4. The square root of that is 3.067. But on the way down, I would have chosen the negative root. On the way up, well, it's positive clearly. So the speed the kid left the floor with, rounded to 2 sig figs, is 3.1 meters per second. So I hope that that is helpful. I hope that you can see that sometimes breaking a problem in half and just starting in the middle gives you a number that wasn't really there but is true. You know the velocity at the top is 0 because that's the point where they've stopped going up and have yet to begun coming down. They're not moving for a brief instant. That's a good place to start when you're dealing with problems like this that are symmetrical in the up and down direction.